In this chapter, we're going to get into thermochemistry, and we're going to start off by going over some definitions and define a few terms related to thermochemistry. So thermodynamics is the study of energy and the transformation of energy from one form into another form. Thermochemistry specifically is the study of the relationship between chemical reactions and changes in energy. So we will look at the energy changes that occur when we break down reactants and form products, and whether we require energy for that overall process or whether we release energy. So for example, you're used to seeing this part of the equation. We've looked at this equation several times, where we have two hydrogen molecules react with one oxygen molecule to give us 2 molecules of water. But in thermochemistry, we also look at the energy change that occurs during this process. And in this case, energy is released, so we think of it as being one of the products. Energy in thermochemistry is defined as the capacity to supply heat or do work. And sometimes we kind of use the terms heat or energy interchangeably because heat is thought of as a form of energy. At the point where the temperature of a substance is uniform throughout, and there is no energy flowing from one point to another, we call that thermal equilibrium. So at that point, both sides have the same amount of heat energy, so there's no heat energy flowing from one side to another. So there's several different types of energy that we can define. There are two main types that we're going to focus on here. One is potential energy. Potential energy has to do with the energy that is stored in an object because of its position. So for example, our ball that's sitting at the top of a hill here. If this ball were to be pushed or nudged just a little bit, it would roll down the hill. But since it's just sitting here, it has potential energy. A fuel also has potential energy. If you burn it, it will release more energy. The other type of energy that we're going to talk about is kinetic energy. Kinetic energy is the energy due to the motion of an object. So for example, our runner over here running has kinetic energy. A car driving down the street has kinetic energy. Anything that is moving would have kinetic energy. If our ball up here is pushed a little bit and starts rolling down the hill, then instead of potential energy, it would now have kinetic energy. The SI unit of energy is the joule, so that's the standard unit of energy. The joule is actually an abbreviation. It's an abbreviation of kilograms times meters squared over seconds squared. So I don't require you to have this memorized, but just be aware that the joule is an abbreviation. A unit that you might be more familiar with is the calorie. So 1 calorie is equal to 4.184 joules. So the calorie that you're familiar with is actually a calorie with a capital C, which is actually equal to 1 kilocalorie. So if you remember your metric prefixes, kilo means 1,000, so that's 1,000 little calories. So when you see calories on food packaging, that's actually referring to kilocalories, which is 1,000 calories. To define some more terms related to thermodynamics, when we talk about energy transfer, we usually talk about things from the point of view of the system. So the system is the part of the universe that we focus on. It's whatever object or reaction we're focusing on when we're talking about the energy transfer. Anything that is around the system, anything that is part of the universe but not part of the system, is considered the surroundings. And of course, the system and surroundings together make up the universe. The first law of thermodynamics can be explained as it's really a law of conservation of energy. What the first law of thermodynamics tells us is that the energy of the universe is constant. We can change the form of the energy. We can go from potential energy to kinetic energy. We can burn chemical energy to use that to transfer to mechanical energy and so forth. You can transform the form, but you cannot change the amount of energy. So when you transfer energy, any energy that is gained by the system has to be lost by the surroundings. Or if energy is lost by the system, it has to be gained by the surroundings. So whenever you're looking at a change in energy, the change in energy for the system is equal and opposite to the change in energy for the surroundings. So when we talk about heat or work going into a system or being done on a system, or heat going out of a system, we define things as positive or negative based on whether it is put into the system or whether it leaves the system. So the symbol that we use for heat is Q, and Q refers to the quantity. The quantity of heat. So when we put heat into the system, Q is greater than 0, so Q is positive. When heat is released from the system, heat leaves the system. Q is less than 0, so Q is negative. Similarly, when we do work on the system, work is positive. When work is done by the system, that's negative. So if we're doing something to the system or we're putting something into the system, that's overall positive. If something is being released from the system or the system is doing something, that's considered negative. So signs in thermochemistry are not showing greater than or less than. They are showing whether something was done by the system or to the system. So for example, negative 57 kilojoules of heat is not less than positive 57 kilojoules of heat. They are just different directions. The positive 57 kilojoules of heat would be put into the system. The negative 57 kilojoules of heat would be released from the system. But we would not say in thermochemistry that is not true, because the signs have nothing to do with the value of the number. They have to do with the direction of the energy. When energy flows out of a system, that's called an exothermic process. So in that case, Q is negative. because we're releasing heat from the system, or releasing energy from the system. When energy flows into a system, we call that an endothermic process. So in that case, Q is positive because we're putting energy into the system. So as I said, Q is the quantity of energy transferring, or sometimes we think of that as the quantity of heat that transfers. So we have to put energy in order for a change of state to occur. So we talk about back in chapter 1, if we go from solid to liquid or liquid to a gas, we talk about what those changes of state are called. If we're going from a solid to a liquid, or a liquid to a gas, or from a solid directly to a gas, we have to put energy in. So those changes are endothermic. So if you're putting energy in, which you have to in order to go from a solid state to a liquid state, which has more energy, to a gaseous state, which has even more energy, those processes are all going to be endothermic. If we're going in the other direction, the liquid state is lower energy than the gaseous state, so we're going to release energy going from a gas to a liquid and going from a liquid to a solid, so those changes are exothermic. When we calculate the total change in internal energy, that is calculated as the change in internal energy is equal to the sum of the heat plus the work. So if you add those two values together, that's the total change in energy. Work in thermochemistry is also defined as a form of energy. Specifically, work is the energy required to move an object through a given distance. So there's two pieces of this definition that are important. One is that you have to move an object, and the other is that you have to move an object over a given distance. So if you push on a wall and the wall doesn't move, you haven't done any work. It doesn't matter how long you push on it or how hard you push on it, unless you get the wall to move. In thermochemistry, you haven't actually done any work. So we can express that as an equation as work is equal to force times distance. So W is the work, F is the force, and D is the distance. We can also think about work in terms of pressure volume changes. So if we keep pressure constant and only look at a change in volume, work is equal to the negative of the pressure times the change in volume. And pressure is force per unit area. So this is really just another way of expressing force over distance. So if work is done by the system, that means energy is lost by the system. The system gives up some of its energy to do work, which is where the negative sign here comes from. Another term that we use quite frequently in thermochemistry is enthalpy. Enthalpy is the sum of the internal energy and the pressure volume product of a system. Now that seems like a lot of words that don't really mean much. And really we don't use enthalpy by itself all that often, because we can't really measure enthalpy. What we focus more on is the change in enthalpy. So the change in enthalpy is expressed as delta H. This little triangle symbol here is the symbol delta, and it refers to a change. So the change in enthalpy is the energy that's either absorbed by reactants for an endothermic reaction, or the energy given off by products in an exothermic reaction, assuming that the reaction is carried out at constant pressure. So we're really referring to an energy change, and oftentimes we kind of use enthalpy, the change in enthalpy, interchangeably with a change in energy, even though they don't quite mean the same thing. Sometimes we refer to this delta H also to kind of mean heat. So when we're doing this at constant pressure, Q is equal to delta H. So this kind of relates the equations that we've talked about already. So just like our other quantities, when the reaction is endothermic, delta H is positive. When the reaction is exothermic, delta H is negative. We can define enthalpy in relation to physical and chemical changes as well. So the enthalpy of fusion is the amount of heat necessary to melt a substance without changing its temperature. So melt, you should recognize this word as a solid to a liquid. Fusion is a term that we use for melting in thermochemistry. So we're talking about the amount of heat that we need to go directly from a solid to a liquid without increasing the liquid's temperature. So it's kind of hard to visualize practically, because a lot of times when you melt a solid, you end up adding enough energy that it also increases its temperature. But in reality, we have to add a certain amount of energy just to go from a solid to a liquid, and then we have to add another amount of energy to start increasing the temperature. So if we could somehow, in theory, measure just the energy needed to go from a solid to a liquid, that would be the enthalpy of fusion. The enthalpy of vaporization is the amount of heat required to vaporize a substance without changing its temperature. So vaporization, we know, is liquid to a gas. So again, we're talking about just the amount of energy we need to go from a liquid to a gas and not increase the temperature of the gas. The last term is enthalpy of sublimation. The enthalpy of sublimation is the amount of heat that's required to convert a substance from a solid to a gas. So that's our definition of sublimation, without going through the liquid phase. So going from solid to liquid to vapor is endothermic. So delta H for those processes is going to be positive. If we're going back in the other direction, going from a vapor to a liquid to a solid, those are going to be exothermic, so delta H for those is negative. So we're actually going to stop here, and we will continue in some of the later videos with some more thermochemistry and get into some calculations here.